Today we're going to learn about identifying exponential behavior. Exponential functions do not have constant rates of change. A constant rate of change means that the increments in which the numbers are increasing stays the same. For example, if we had a sequence of numbers such as 4, 7, 10, 13, then we can count each interval to see that each one is an increase in 3. Now, exponential functions don't work that way. The intervals are always going to keep increasing in value. So for example, if we had 4, 7, 12, and 21, the first interval would be 3, the second interval would be 5, and the third interval would be 9. Here we can see that the rate of change is not constant. It first starts at 3, then from 3, we up the rate of change to 5, and then to 9. Now let's take this pattern on the left-hand side and figure out if it's exponential or not. So we have 64, then 32, then 16, then 8, 4, 2, 1, and 1/2. From 64 to 32, we're divided by 2. From 32 to 16, we're divided by 2. And as you can see, throughout the sequence, it's going to stay the same. Now, this sequence is exponential, but you might wonder why it's exponential if the value stays 2 the entire time. Well, it's because dividing or multiplying by a constant is not a constant rate of change. It's actually exponential. For an exponential function, the rate of change for addition and subtraction cannot be equal to c, some constant integer, while multiplication and division can have a constant integer as the rate of change. One of the best ways to proof check that the graph is exponential is by graphing it out. Now let's say that each of these intervals is 16 on the y and 4 on the x-axis. So at a value of x is equal to 0, we're going to have 64. At a value of x is equal to 2, we're going to have 32. At a value of x is equal to 4, we're going to have 16. And then 6 is going to be 8. And 8 is going to be 4. And from here on out, the graph is going to get infinitely closer to 0. Again, we see that the line has the same shape as an exponential decay. And it's nonlinear because it slopes. So that's how we know it's exponential. Now that I've changed the function, let's graph this one instead and see if it's exponential or not. Let's first identify the rate of change of the sequence. 14, 12, 10, 8, 6, 4, 2, and 0. As we can see, the increments are -2, which means that this function is not exponential. Now let's graph it. We're going to have increments of 4 on the x and y axis. And at 0, we're going to have 14. At 2, we're going to have 12. And so if we were to graph this, it would look something like this. A straight line. Clearly linear, which means it's not exponential.